In this tutorial video, I'll explain how to compute the continuum tortuosity of a material using the PuMA software. Assuming the installation has been complete, the PuMA software can be run by simply typing PuMA in a terminal window. At this point, the PuMA graphical user interface will open, and the first step in computing the effective tortuosity of a material is obviously choosing a material, creating the computational domain. That can be done either through microtomography import or generating an artificial geometry. In this case, we'll generate a packed sphere bed with a domain size of 256 in each direction. This is pretty small, but the reason I'm doing that is because this is a laptop and I want it to run quickly on the case for the purposes of this tutorial. The next thing to specify is the radius of the spheres. In this case, we'll choose 5 plus or minus 1. The voxel length of 1 micrometer, and porosity we'll choose 0.5. Finally, you can choose whether or not to allow the spheres to intersect. If this is not checked, then it will be much slower since it has to try to fit spheres into spaces that haven't been occupied yet. So we'll allow them to intersect to make this faster. And you can see that what we're left with here is a packed sphere bed that has about 31,000 spheres, I think is what it says. In order to then compute the effective tortuosity, we need to go to Material Properties, Tortuosity, and select Finite Difference. We then need to select the grayscale range of the void phase. Since this is an artificially generated material, it means it has a void phase between 0 and 127. This is because a 128 threshold is used to segment the material, meaning that if we were selecting the material phase, it would be 128 to 255. But since these values are inclusive, to select the void phase, it is 0 to 127. The next is the accuracy of the iterative solver. If you've watched the tutorial videos for the conductivity, the both electrical and thermal, you know how this works. The accuracy is an cutoff for the iterative solver. This value is typically taken to be about 1e to the minus 4. Finally, the number of threads is selected, which is usually the number of physical cores on the machine. In this case, we'll use a value of 4. Finally, the directions for the simulation. We'll do all three. This is a isotropic material, or at least it should be, so we would expect that the tortuosity values are the same in each of the three directions. Finally, save resulting map means we save the steady state concentration profile. This will be saved under the PuMA run folder in the conductivity maps category. We'll go ahead and check that and begin this calculation. While the calculation is running, I want to briefly explain how the domain size affects the speed of this computation. Obviously, larger domain sizes will significantly increase the speed, but also the domain size matters for the fast Fourier transforms. Typically, 2 to the n is the optimal domain size for the speed of the fast Fourier transform. You want to minimize the size of the prime factors, which means that 400 is fine, 800 is fine, 1000 cubed is fine, assuming your computer has enough RAM to handle that size. But something like 2 to the n minus 1 is usually pretty bad, or 2 to the n plus 1. So typically you wouldn't want to do something like 1001 cubed because it would slow down your simulation pretty significantly. So the simulation is now complete, and we can see the tortuosity values in the x, y, and z direction are shown. And as we would expect, since this is a fairly isotropic material, the tortuosity values are essentially exactly the same in each direction. 1.712, 1.712, 1.722. So it's extremely similar. And that concludes the tortuosity aspect of the PuMA software. For more details on this, please reference the PuMA user manual if anything here is unclear.